Okay, so we were talking about the reproducing kernel Hilbert spaces, and we did some review of functional analysis. A particular result of interest is this Rees representation theorem that says that if you have a Hilbert space H and you have a bounded linear functional on the space, then there exists a unique element in the Hilbert space such that you can write this linear functional as this element inner product with a generic element in the RKHS. That's how you create all linear functionals, basically. So there's a one-to-one mapping between all bounded linear functionals and the Hilbert space itself. So and then we just define the RKHS or an RKHS to be a Hilbert space of functions. So a Hilbert space is an abstract construct. An RKHS is not like an abstract Hilbert space, but it's more of a concrete space of functions that has a Hilbert space structure. So there is an inner product with respect to which we have a norm and with respect to which we are complete. And then we have the main property besides this is that the evaluation functionals are continuous, or you can say bounded, right? And the point being, this evaluation functional is a linear functional. So you fix x, and this evaluation functional just evaluates every function at that particular point. So as f varies in h, it's easy to see that this is actually a linear functional, but it could be unbounded. And the point is that in an RKHS, this is a bounded functional. And then from this fact, it's easy to see that whenever a sequence of functions converges in the Hilbert norm in an RKHS, then it has to converge pointwise, because that's the meaning of continuity of the evaluation functionals. So we saw an example where you have a Hilbert space structure, you try to complete, like form a completion of the continuous functions of 0, 1, C, 0, 1 under this L2 norm. So the completion in measure theory is well studied. That would be like the L2 space of functions. But it's not an RKHS. It can be made into an RKHS. And the easy sort of situation was like providing counterexample sequence of functions such that it converges in L2 to 0, but like they don't pointwise converge to 0. So there's this point that they all are equal to 1 at. And so this because this consequence fails, so it can't be made into an RKHS, at least with respect to this norm. And then we saw the Sobolev kernel, Sobolev RKHS, in which it's like the space of functions that are absolutely continuous on 0 to 1, and the derivative is in L2. And you have one boundary condition. You could have required 2 boundary conditions that would change the RKHS a little bit. So with this with f prime in L2, we can define this inner product. So this is well defined because f and gr have derivatives in L2, and then you can verify that this is really an inner product. And we sort of last time we showed that the evaluation functional is bounded, continuous, and the norm of that functional is bounded like that. That's by Koshi Schwarz. And we also argued that this space is a Hilbert space. So Koshi sequences converge. And so it's really an RKHS. So we'll come back to this today. the main property that we talked about, that the evaluation functionals are continuous, implies by Ries's representation theorem that I can write evaluation as an inner product with some representer of evaluation. So k of x, for every x, there is a k of x in the Hilbert space, such that if I want to evaluate f at x, I just take the inner product of f with that representer. So this is a very powerful idea because usually you don't look at evaluation as an inner product. But once you look at it like that, a lot of things in sort of traditional Euclidean analysis just automatically extends. That's the main power. And then, so there is this unique representer, and I can define a kernel, a producing kernel for H because it has two arguments. So there is an x there, but it's also a function, let's say, of y. So this defines a kernel like a bivariate function. And given this bivariate function, we can write this property that we had there, that this is equal to f as just f of x is inner product. This inner product is in the Hilbert space, right? Inner product with the kernel. If I fix the kernel in one argument, look at it as a function of the other argument. This is in RKHS. Take the inner product with f that evaluates the function at x. Okay, and then we also see that I can apply this result. This is just k of x. If I apply it with f being k of y for some y, this would be like kyx. Or let's do, yeah. And I can do it the other way around as well. I get kxy. So kxy and kyx are the same because the inner product is symmetric. And like it follows that kxy can be written as the inner product of x and kx and ky. So this gives a factorization representation of the kernel function. It shows that it's symmetric and also shows that it's positive semi-definite. So we went through this last time. What it means is, just to remind you that if you take a collection of functions, like a set of points, and evaluate k at pairs of distinct j, like xi and xj for all pairs of I and j, you get a symmetric matrix. So the function k is called the kernel. If it's so if it's symmetric in PSD, positive semi-definite, and positive semi-definite means that these matrices are positive semi-definite for all choices of the sequence and for all m, basically. So a kernel is just a symmetric positive semi-definite bivariate function. And it turns out that the reproducing kernel of an RKHS is indeed a kernel in this sense, because this representation that we have over there, this implies PSD-ness. So we did this last time. So if you want to show that that matrix is positive semi-definite, you would look at these summations, and this is just summation ij, ai, aj, inner product kxi, kxj, and it's not hard to see that this is just ai, kxi, norm squared. These are all in the Hilbert space, and so this is positive semi-definite. So this representation gives you that, okay? So the key result that we wanted to talk about, okay, so maybe we didn't talk about this. Let's see what the kernel for the Sobolev one is. So this is remember, this is the Sobolev space. And I can write every function that's in the Sobolev space as, this is the fundamental theorem calculus, so f of x can be written as integral from 0 to x ft prime dt. So f prime exists almost everywhere, and then it is it's in L2, so it's in L1 in fact as well. So this exists, and we have we also have f0 equal to 0. You can see from the fundamental theory calculus that this holds. Right? So this would be like f of x minus f of 0, and we have this boundary condition. And so I can write it like that. So this is the same as this. And then if you recall, the inner product was basically this inner product with the derivative of something. So if I write this as some function prime t, then this would be the inner product of f and kx. This is the Hilbert space norm. So if I manage to find a function whose derivative is this, then this would be the representer evaluation. And that would be my kernel, that defines my kernel. And so in order to do that, you just have to find a function whose derivative is derivative is 1t less than or equal to x. And you can plot this, right? So this function looks like, so it's 1 before point x, and it's 0 otherwise. That's this function as a function of t, right? So if you integrate, the integral would be like, this goes up linearly and then stays constant. Okay, so that would be basically the minimum of t and x. Okay, and then I have to add a constant to it because this is an antiderivative. So that's the general form. So a function whose derivative is this is going to be, yeah, so this is differentiable everywhere except this point, but that's okay for us. So we want something that's differentiable everywhere, almost everywhere, and the derivative matches this almost everywhere. And this is the case, then you would enforce the boundary condition. So I want basically kx0 to be 0. Right, and you can see from this picture that the only way that I can get 0 is that if there's no constant, basically, otherwise shift it up. So this has to be 0 by the boundary condition. So viewing this as a function of the two variables, that's the kernel. So I can write the kernel. The kernel is the min x and y. So you can see it's symmetric, and a consequence, for example, is that basically this is going to, because this is an RKHS and the kernel matrix is the reproducing kernel, sorry, this kernel is the reproducing kernel of an RKHS. It's a positive semi-definite function. Okay, so if I take, for example, xi's, basically any sequence, the kernel matrix is positive semi-definite. So if I have something like this, then the min xi, y, xj, this is a positive semi-definite matrix. So that would be like 1 over n. The minimum would be, so it's like going to be 1, 1, 1 everywhere. And then here it's going to be, I believe it will be something like this, 2, 2, and then 3. Right, something like that. And so this matrix, for example, is positive semi-definite without doing any calculation and any other sort of form of this. Questions? Okay, so there are other kernels. If you take the x to be Rd, the linear kernel is just the inner product of x and y. So they're like the homogeneous polynomials. This is like this to the power m. So this RKHS, we'll talk about the Moore's result more. Every positive semi-definite basically function, every kernel generates an RKHS, and that RKHS is unique. So if these are positive semi-definite, which you can verify they are. So this is easy to show that it's positive semi-definite. This might be a little bit more tricky. And this, for example, produces polynomials of degree m. This is like also like, this is homogeneous polynomials, inhomogeneous polynomials. And this is a Gaussian kernel. Proving this is PSD is a little bit harder. But you can use Fourier analysis. Okay, I'll come back maybe to these. So what I want to do now is, so the first result that we can talk about is that if H is an RKHS, then the linear span of these representors is dense in H. So what it means is that I can approximate any function in H by a linear combination of finite number of these. So if I form, so if I have f in H, then for every epsilon bigger than 0, there exists x1 up to xn for some n, and let's say alpha 1 up to alpha n. This is in X. This is in R, such that summation alpha I k xi minus f in Hilbert norm. This is less than epsilon. Okay, but I might have to change these points and these coefficients if I change epsilon and unchange f. So the linear span of this is not a finite dimensional set. So the first thing to note is in the proof is that the pair of this is equal to the 0 function, like the trivial subspace, and this proves it because we showed that, or argued that in a Hilbert space, a subset is dense if and only if the orthogonal complement is the trivial subspace. So how do we show that this is true? That's the proof, basically one line proof, but you just have to verify this. So f belongs to kx, x and x, per if and only if inner product of f and kx is 0 for all x in x. Okay. So what does this give us? Yeah, so this is equivalent to, by the representer, sort of by the reproducing property, this is equivalent to this. Okay, so this just says that f has to be identically 0. Okay, it's a very like immediate consequence of the reproducing property. So the purpose of this is the trivial subspace, so this has to be dense. Another way of saying is just the closure of the span is H. That's just exactly what density means, and the closure is in the Hilbert norm. Okay, so okay, so question. So this is the main result that I basically pointed out to last time. So every kernel, basically every symmetric bivariate positive semi-definite function has a unique RKHS. So if you find a kernel, then it generates an RKHS on X with that kernel being the reproducing kernel of that RKHS. So this is Moore or Moore-Aronszajn. I mean, it's hard to pronounce. But that's the guy that basically wrote the classical paper summarizing properties of RKHS. So this result is proof something like, I mean, there are different ways of proving it, but basically you work with the span. So we know that from that result that if you have an RKHS, and if this is the reproducing kernel, then the span of these is dense in the Hilbert space. But the issue is that we don't have the Hilbert space yet to take the closure with respect to. So you start from this span is well-defined, this W, and you try to sort of create the Hilbert space out of it. Okay, so you have to take the closure, but it's not clear how to take the closure because you're not in the RKHS itself. So to start from this, define inner product on W. I'm using star here. So if you have a finite, so span here means the set of all finite linear combinations. So if I have two finite linear combinations, these are finite linear combinations of elements. If you take the inner product, we define the inner product to be this other side. Okay, that's what happens if you are in RKHS, because if you remember, because by the properties of so if we wanted to define an inner product by the properties of the inner product, let's write it like this. This has to be sigma alpha I beta j inj inner product of kxi and kxj, right? Whatever inner product you put here, because inner products are bilinear. And we know that if you're in an RKHS, this, and then this is the reproducing kernel, this has to be kxi xj, okay? So we define the inner product like that on this linear space. And then if you extend it, we're going to keep this definition, so it at least works on that space. So on this space, I define this inner product. It's a couple of things that you have to verify is that it's well-defined in the sense that if I have a single function that can be represented as these linear combinations two different ways, and then this one as well, for example, multiple ways, then when I define it like this, the inner product doesn't change. And the way to show it is that if you have a linear combination of these that's identically zero, then if you take the inner product of f with respect to any w in W in this sense, the inner product would be zero. So that would show the uniqueness. So as an exercise, try to like the well-defined this. As an exercise, try to show that. And then from this definition, you can see if I just take one of these summations to be, so what happens if this only contains like kx, okay, that would be like this would be the summation. So from this, it follows that. So if f is equal to alpha I kxi, then f inner product with kxi would be just summation alpha I k xi and x by this definition, right? But this is just f of x, right? Sorry, what I'm saying is f of x. If you look from this definition, when I do this, if one of these is just k of x, I would have like k of x here. This summation would just be alpha I k xi and x, right? And this is nothing but f of x. Why is that? Yeah, because f is just this, and then kxi is just, f of x is basically, if you put the argument there, it's just you're evaluating that x, so that's how. So this reproducing property holds over this space with this inner product. So we have everything in place. The only issue is that, so it's an inner product space with the reproducing property for this inner product, like this kernel representors with respect to inner product. The issue is that it's not complete necessarily. So then we can complete it. There is like an abstract completion. So I can take equivalence classes of Koshi sequences as members of this abstract space, then I would make it into a Hilbert space. The issue is that these equivalent classes are not necessarily functions, but we want to argue that they can pick unique representors from each equivalence class. So we're actually dealing with the RKHS of functions, and then their producing property extends. So that's like different ways of doing it, but this is one way. So we show that every element of the completion is in fact the function. This is, for example, as opposed to the case where you do the completion of C01, which is like the L2 norm, you get the L2 01, then the members are really equivalence classes. You can't sort of identify a single one as a useful function. You can like do it, but in that theory, just, for example, evaluating functions in L2 at a point doesn't make much sense because you can just manipulate them over a set of measure 0 and they're equivalent in a sense. Here, it's not like that. We can like find a continuous basically function. So the way to do it is like let H be a mirror of H, this new completion. So H at this point is not, we don't know if it's a function. It's just a member of that equivalence class. Or actually, it's just the equivalence class itself. And let's say Fn is a sequence of functions in W. That's the ground states that we started with. And assume that this is a Koshi sequence with Fn converging to this H. So this Fn's we are like viewing as both the functions and also the equivalence class. So these are going to be like mapped to equivalence classes when you go to the completion. So in that completion, Fn is converging to H. If it's a Koshi sequence, there is an H that this converges to. That's because H is Hilbert space. Now, by Cauchy-Schwarz inequality, we have first we have this equality for any Fn. So why this like equality holds? Yeah. So this had the producing property with respect to that pre like Hilbert inner product. So we have that, and then we have the Cauchy Schwarz inequality, where so when you do the completion, basically the norm and the inner product over this space is preserved. Okay, that's the thing to note. So I can use the Cauchy-Schwarz inequality, which holds in any like inner product space, like before even completion. So that would give me the norm of X with respect to this inner product, which is like root. You can verify that this is that, and then you get the norm of this. And you can put a star here, or you can drop the star because the norm would be the same in W and in the completion. So because your Cauchy in H, this norm converges to, so this is converging to 0 as n and m go to infinity. So this says that the sequence Fnx is converging. Fn is pointwise convergent. Okay, because it's pointwise Cauchy, so it has to be pointwise convergent because it's like a real valued sequence. And so the limit is well defined. So for every x, there is a limit because this is a Cauchy sequence for every x. So I define the limit to be h of x. So now that I have a function, and then usual argument shows that this is independent of the particular Cauchy sequence that you pick. If there are two Cauchy sequences that are in the equivalence class, same equivalence class, they have to converge to the same pointwise like function. Pointwise, they have to converge to the same function. So, okay, so for basically, okay. In other words, so basically, that's what I'm saying is that the best way to do it is like you pick H in this. There is a Cauchy sequence that converges to it, and so what we showed is that for this equivalence class there is a representation, like a functional representation, which is pointwise. So for every for every other, let's say H in that particular equivalence class where this guy lived, this limit is the same, so you get the same function by this procedure. The next thing is to verify the like the reproducing property or the evaluation functionals being bounded. So let the inner product be the inner product on H, then let F and H be as above. Then we have the sequence of equality. So there's this equality. So why this is true? Inner product is continuous in the first argument. So yeah, so Fn is converging to H in the Hilbert norm. So that's the so this is the inner product. So both are in the RKHS or the completion. We don't know if it's an RKHS yet. And then this holds because Fn is converging to H. How about the second one? The second equality is because we extended this inner product by completion. So both of these elements are in W, right? So it has to be the same as the star. So how about this next step? That's the evaluation holding on that pre-Hilbert space. And then this is the limit is H of X, that representation, like the representer that we picked. So this is showing that H inner product just produces that representer. So in a sense, basically every equivalence class can be identified with a point-wise function, basically. And then this representer result holds. So this is showing that K of X is in fact the representer evaluation in H. And so H is an RKHS, and this has to be the representing kernel because that's the case. Then the uniqueness we'll talk about. The fact that this is the unique representer follows because every RKHS can have just a unique kernel. Okay, so it's a little tricky, but the point is there is a way that we can define the RKHS by first defining inner product of space over the span, which has the right inner product, and then that inner product will give us the reproducing property over the space, and then we do the completion, and then in the completion we can show basically because of this representer property, you can already see the representer property together with Koshi Schwarz tells you that these have to Koshi sequences have to converge pointwise. So if you look at an equivalence class in that completion, all the ways that the Koshi sequence converge to a single, basically all the elements in that equivalence class can be represented by a function. And then you show that the reproducing property extends to that function. There are other ways of doing this, which might be a little bit cleaner, but this is, I think this does it. Okay, sounds good. So every kernel produces an RKHS, and that's how you construct it. The reverse is also true. Every what the other is saying is that if you give me an RKHS, sorry, if you give me a kernel, so what this result is saying that if this is the space of kernels, this is the space of RKHSs, and if there is a map that maps, I don't know what we should call it, psi that maps kernels to RKHSs, that this result is saying that psi is onto. Oh, sorry. What does it say? So it says for every kernel, there is an RKHS. So actually this says this is a function. Is that? What does it say about the mapping that maps kernels to functions? Sorry? Defined? Yeah, so that's like the psi is a function. Like defined on all kernels, basically. Yeah, defined on all kernels. What we can show is that this psi is injective. So if you have two different kernels, then it has to do different RKHSs. And the fact that this onto, how do we show that this is onto? If we just show that for every RKHS there is a kernel, because every RKHS has a reproducing kernel. So we show that there is a map from this to this, there is a map from this to this, and this map is injective. I think that's enough to show that there's like a bijection. That's what we sort of do. So this part says that that's sort of psi is injective. Psi from previous slide. So in order to show that, you show that if you have two RKHSs with possibly different kernels, if the kernels are the same for all x and y, so this is the reproducing kernel of the RKHS, then the RKHS have to be equal and the norms have to be equal. So in order to prove this, again, that's the, so we take this notation. So the representer is the same for both of the, because the kernels are the same, we can define the k of x to be the same. And then we look at the span of this k of x's. We know that w is dense in both, right? So these are dense in both spaces. Then it's easy to verify that the norms are the same for every f in w, because if you recall, the norms are just defined in terms of, on that space are defined in terms of the values of the kernel. So, right. So the inner product basically and the norms are the same for every functions in w. So if f is in H1, then there exists a sequence in W that converges to f in H1 because W is dense in H1. So Fn is Koshi in the first space, right? W with this norm. Hence it's Koshi in W with this norm because the norms are the same over that W, right? So there has to be, because this is dense in H2, there has to be an element in H2, G, for which this converges to G in H2. And so because these functions converge to f and g in these spaces, they converge pointwise in each case. So Fn converges pointwise to f because the convergence in H is stronger. So Fn converges to G and to f pointwise. And because the pointwise, these are the pointwise limits of the same sequence, they have to be the same. So fx and a gx has to be the same. And this holds for basically, so what do we show? We show that if f is in, so if f is in H1, because g is in H2, f is equal to g, so f has to be in H2. So every f in H1 is in H2, and the reverse argument that also like by symmetry holds, so that the two are the same. And then furthermore, since the norms are equal on a dense subset, they have to be equal everywhere. Right? So this is in both the spaces, and the two spaces are the same, and this is basically in both. And so the norm sort of extends to both. Okay. Question? So basically what we showed is that this map is injective. We showed that just the well-defined over all kernels. We showed that for every RKHS there is a kernel that's like the reproducing kernel. So this map is like a one-to-one correspondence. So there is a one-to-one correspondence between kernels and RKHS. Okay, this is a fairly interesting result. Now let's see what we can do with RKHS. So there are interesting things that we can do with these. The first thing to note is we can sort of define an interpolation problem. Suppose I have a collection of data points, x1, y1, xn, yn. So think of the training set for a regression or classification problem. What I can try to do is try to find a function that maps x perfectly to y. So this is the interpolation problem. So I want a function that maps xi to y, I for all I from 1 to n. If I restrict my f to be in H, and if H is finite dimensional, there might not be solutions. But if f is infinite dimensional, there are often many solutions, because this defines or imposes n constraints, whereas f has like infinite degrees of freedom. So I get many choices. What we can do is we can try to minimize the H norm, the minimum norm solution. And for example, for the solve of a space, the norm, if you recall, is like the L2 norm of the derivative. It measures the roughness. So this finds something which is the smoothest, in a sense, in the space that interpolates the points. So it's like finding the smoothest interpolant. So it's a very natural, like intuitive idea in practice. So the point is that this problem, although it's infinite dimensional, can be reduced to a finite dimensional problem as follows. So if you define this normalized kernel matrix, so it's an n by n matrix whose elements are k, xi, xj divided by n. And if you look at the y's as just the vector, so this k kernel matrix is like 1 over n, k x1, x1, k x1, x2, k x1, xn, right? So, and then k xn is a symmetric matrix, xn, x1, k xn, x2, k xn, xn, and then the y is just y1 up to yn. So what it is saying is that the problem 4 has a solution if and only if y is in the range of k. And in that case, there's a unique optimal solution. There's a single solution which can be written like this. I can write the interpolant as this, where alpha, so this is not correct. So this should be alpha hat. So alpha hat is alpha 1 up to alpha. So this is basically in the span of those kernel functions, basically, right? And the coefficients are defined or determined by this linear equation. So you have to solve this linear equation. Basically, if k is invertible, then you can invert it. If not, you can see, because the assumption is that the y is in the range of k, this always has a solution, even if k is rank deficient. But if k is n by n, if it's invertible, you just get alpha hat k inverse y. But in general, you just have to solve this equation, and you get your result. Okay, so how do we prove something like this? What do you see? This is an example. Let me just show you the example from the HDS book. So if you, for example, look at the polynomial kernel in R, right? So 1 plus xz to 12. This is the kernel generates polynomials of certain degree. Most likely 12. And so if you do this operation with this kernel, then it would fit a polynomial of certain degree, 12, to these data points. And if you do it with the minus t kernel plus 1, if you do add a plus 1, we'll talk about this. This would just free the boundary condition. So you now have f0 can be anything. So this kernel, you'd get this interpolation. And it's easy to see from this representation that if you're dealing with a minus t kernel, f hat would be can forget about the root n, it's just there for simplicity. You get alpha hat I, 1 plus min, let's say x and xi. Right, and if you plot this, because the min kernel is like this, just goes up and flattens. If you add a bunch of these shifted, you can see that would be like a piecewise linear function. So the linear, like the minimum norm interpolant in the solval of one kernel would be just a piecewise linear interpolant. That's the sort of smoothest that you can get using a first order solval of kernel. If you do to higher order solval of interpolants, you get a smoother function. Okay, but this is interesting. So this just shows that, for example, what this is saying in this case, so for kernel k xy being like 1 plus min xy, what this is saying, we are solving like minimum integral. Okay, so let's do this. So you're solving a non-trivial problem. So if the kernel is like this, so the problem is minimize, the norm would be integral f prime x squared dx from 0 to 1 over f such that f prime is in L2 of 0, 1. There is no boundary condition because of this addition of 1. We'll talk about that. And then fx1 is equal to y1 f xn is equal to yn. So this is showing that the solution of this problem, the function that passes through these points, its derivative is in L2 and minimizes this L2 norm of f prime is like a linearly, piecewise linear function that passes through these points. It is a non-trivial fact, but the theorem of RKHS easily gives you that. Okay, sounds good. So how do we prove this? Let's try to see if we can prove it. So the main point of all these results is that I can always, so we'll define this as span. Remember, so let's call this W, the span. It's not W, let's call this something else, I don't know. V to be the span of x, kx1 up to kxn. So we have these data points, and we anchor the kernels at these data points, okay? So, and the way you're writing is just a span of kx1 dot kxn dot. And from the result, you can see that the claim is that the solution is the span of these guys, right? So want to show that f hat belongs to V, okay? So this span is a linear, so this is a closed linear subspace of the RKHS. So why is it closed? I'll name people. Why is it closed? Because it's finite dimension. The limit, any sequence, so you want to show that if you have a sequence of functions that converge, it has to converge to something like this. Why is that? Okay, so let's see. So you'd have like a sequence, but it would be like alpha, like sequence by nu, let's say. Alpha I k xi. So you know that this converges to some, as nu goes to infinity, converges to some f in the Hilbert space. Right? You want to show that f is in there. So why? Why can I take the limit inside? Right. So yeah, you can do pointwise limits. So you have this is equal to x. Sorry, this converges to. Yeah. So you'd have f of x is like limit. And then you say, I'm going to do. So this is just in. So individually. One question is that do these coefficients converge? Have you argued that they converge? Yeah, fine, yeah, but the question is that do these individual coefficients converge? You have to sort of argue that the alpha I nu converges for every I, and if it converges, I can move this inside. Right. Alpha i's are numbers. What do you mean by norm? That would be like alpha I. So it would be summation alpha I nu alpha j nu k xi xj. So that would converge to the Hilbert norm. That's true. But it doesn't tell you that these converge. So you can think about this argument, but it's just a finite dimensional subspace of any Hilbert space is closed. I mean, it's easier to show probably more generally, but think of the argument. So it's closed, so I can write f hat as, so since this is the case, then f hat can be written as, let's say f1 plus f perp, where f1 belongs to v and f perp belongs to v perp. I can do it for any closed linear subspace. There's an orthogonal decomposition of the space. So this means that the norm of f hat is equal to, so let's pick any f. So pick any f. Pick a generic f in H. Then f can be written like that. And the norm of this guy would be the norm of this guy plus the norm of that guy. That's by the orthogonality, right? So what we are doing is now you're minimizing this norm. So we have two components. So let's see what happens. So if f, assume that f is feasible for the problem. So it means that fxi is equal to yi for all I, right? I can write this as f of kxi equal yi. That's the reproducing property, right? And then this is just equivalent to f1 plus f perp kxi equal yi for all I. So this is assume. So what can I do now? I get F1 now KXI plus verb KXI. Is there a simplification that I can do here? That doesn't help me because that would give me F1 xi is equal to plus f of xi is equal to yi. But I know this because this side is f. That doesn't help me. What can I say about this term? So remember, f perp belongs to v perp, and v is this. 0, why? That's correct. Why is this 0? Yeah, so f perp is orthogonal to yeah, so kxi is in this span of kx1 up to xn, and that's v, and we know that f perp is in v perp, so it has to be orthogonal to all of them. So that's the case. So what we showed is that if f is feasible, then f1 is feasible. And basically the orthogonal component doesn't affect the feasibility. I can add the orthogonal component to any, so if I have f1, then I can add any orthogonal complement to it. I just don't change the feasibility. But then I also know that the Hilbert norm is like this, okay? So it doesn't make sense to add any component in the orthogonal complement because I would increase the norm, right? So you start from any f. If it's the optimal solution, it has to be feasible and it has an orthogonal complement. If the orthogonal complement is non-zero, I can drop it, I'm still feasible, and I can reduce the norm, right? So it shows that the optimal solution cannot have an orthogonal complement, right? It has to be like only entirely a component in V. If it's a component in V, it just belongs to this span, right? Does that make sense? So you start from any f has this decomposition. Like let's say f was the optimal solution. So f hat here. We know that f hat 1 is feasible by this argument. And if this part is non-zero, I can just drop it to 0. So f hat 1 would be the minimum norm solution. That would contradict f hat being minimum norm solution. So from the start, this has to be 0. So f hat has to belong to this span. So the key part is just, you can see writing this equality, pointwise equality as just the inner product. That's the reproducing property, right? So once you have that, this is, so we showed, so this shows that the optimal solution f hat has to belong to V, which is the span of KXI. So then I'm going to write f hat as, I'm going to forget the, so this has to be like this for some alpha, right? Or I'm just going to restrict myself to this class. So what is the norm of f? Hilbert norm of f squared. So I can restrict to functions of the following form. that would be like alpha I k xi inner product with alpha j k xj in the Hilbert space, right? So that would be summation alpha I alpha j k xi xj xi and k xj, right? And so this is, what is this? K xi xj. So I can write this as alpha transpose basically n times k alpha, where k was 1 over n, k x1, xi xj, right? And you can see if I divide by root 1 over root n here, right, I get 1 over n here, 1 over n here, and then this would go away. So that's the reason why we did this. This is simpler now, right? So if f is like that, so I sometimes write it at f indexed by alpha, because given any alpha, I can write this down. If f alpha is like that, then f alpha Hilbert norm is just going to be alpha transpose k alpha. So what we're doing is, so how about the condition that f alpha xi is equal to yi? For all I can write this again as f alpha kxi is equal to yi, right? And this is summation alpha I kxi 1 over root n. 1 over root n comes out. Let's say j kxi kxj. This is equal to yi, right? So this is going to be 1 over root n summation over I, inner product of kxi kxj yj. So this is kxi xj, right? This is alpha I, right? So what do I get? I get, so rewrite this again cleanly. This is alpha I k xi xj. I'm going to divide by n and then multiply both sides of this by 1 over root n. Basically, I get yi divided by root n, I from 1 to n, right? So what is this? This is like the ith row of, it's like basically kij, the ith element of the kernel matrix, right? So what we're saying is like, it's like alpha transpose k, or like, because k is symmetric, this is like k alpha is equal to y over root n, right, by symmetry. Okay, so what we are saying is that the problem reduces to minimum, I can just minimize over these functions where alpha is in Rn, such that f alpha xi is equal to yi for all I, and this is equivalent to minimizing alpha transpose k alpha, because that's the Hilbert norm squared, subject to k alpha equal y over root n. Okay. So if k is invertible, then this problem has a single solution. Alpha is k inverse y over root n, and that's the only possible solution when you try to minimize. There is one single solution that gives you the interpolant. In general, you can show that what I mentioned is true. So definitely the solution has to satisfy this, because that's the basically these equations. And when k is invertible, there's a single solution that would give you the best, like the optimal solution. Otherwise, you get multiple solutions probably for this. You could get, but this is going to be unique. In any case, and then the from this, if you plug it into that, so we see that like the optimal solution, the Hilbert norm squared, replacing k alpha in the objective. So what do you mean by this? So the objective is this, because we calculated the Hilbert norm here, right? Yeah, so the problem reduces to a function. This is the reduced problem. The thing is that this problem is very simple if k is invertible, because it's just, the feasible region is just a single point. Minimizing that would just give you, just give the minimum solution. The solution would be this, and the minimum value would be like y over root n. When you plug it in, would be like transpose k inverse y over root n. So that would be the norm of the optimal solution. Would be y transpose, basically k inverse y divided by n. If this k is not invertible, the only way that this has a solution is if y is in the range of k, and then you can show that any solution basically gives you the same value, alpha transpose k alpha, and then any solution would work. Not sorry, maybe not any solutions, but or maybe any solutions. Just figure out the case where k is not invertible. So when the RKHS is infinite dimensional, usually k is invertible, because k being invertible means that there is what it means for k to be invertible is that no matter what yi's I put here, I can always find a single interpolate. Like there is at least one interpolate. So if the RKHS allows you to interpolate any pairs of points, like pairs of xi's and yi's, for example, the -t kernel definitely does that, because all these piecewise linear functions are in the RKHS. They can always like interpolate for any y's, basically any xi's. There is at least one interpolate. If that's the case, then the k has to be invertible, and then this has this unique solution. Okay, the other cases I'll let you figure out, but basically the problem reduces to solving this. Okay, does that answer your, like, addresses your comments? Questions? Yeah. You're talking about here? Yeah, we chose x1 to xn. Right. Still found some other x's associated with that. That's the issue. So the reason why we did this is because of this condition. Because when I have these conditions, right? So the reason I chose those x's because I have this feasibility condition. And when I write it like this, I get something like that. And in this point, I can say that, so all of this goes true, but the other side, is just if you pick the other points, there's no reason why. So you can always write every f like this, and so f of xi would be equal to this component always, but it's not clear that that xi, but f of xi might not be equal to yi. So there's no, this argument doesn't go through, right? The point of the argument is that it tells you that the feasibility is preserved if I manipulate f on the orthogonal complement, and if I manipulate on the orthogonal complement, I don't change the constraints, but I manipulate the norm. So I can minimize the norm by just dropping the orthogonal complement to 0. If you do it on the other points, there is no connection to the feasibility constraint, so it's not clear Yeah, it's not clear. Can you repeat why K is usually invertible? Yeah, so you can see the invertibility of, if you go, if you follow the argument that we did, this condition is equivalent to saying that it's not equivalent to saying, but this is sort of, there exists an F in the span of KXIs if and only if K alpha is equal to y over root n. Okay, so for some alpha. So if I can solve this equation, then I can find an F in this span. And K being invertible is equivalent to being able to solve this for all possible y's. Okay, so what we conclude is that if the RKHS is such that I can interpolate basically any points, so whenever I give you x1 up to xn, no matter what y's I pick here, I can always find an interpolation. I can always find a solution here. Because if I can always find a solution here, I can find a solution in the span, because the orthogonal complement, as we discussed, doesn't, sorry, you don't see where I'm pointing at. So if I can find a solution to this, I can always find a solution in the span, because the orthogonal complement does not contribute. Okay, so if I can always find a solution for this, no matter what choices of yi's I pick here, then it means that I can solve this equation for all possible y's. And this is equivalent to saying that K is invertible. Right? Fixed x's, as long as you can interpolate all possible y's with these x's, there should be an F in the span such that there should be an F in the span of KXIs that interpolates. And then from that, you get that K alpha has to be equal to y over root n for any y's. And so if the RKHS allows you to interpolate any basically sets of points, then that's equivalent to K being invertible, at least for those x's. And if it's like possible to do it for all possible x's, then it means that no matter what kind of kernel matrices you make out of all possible x's, those are always going to be invertible. It's a very interesting non-trivial fact, which is related to the interpolation, like power of the RKHS. Right? Sounds good. Okay, no problem. Thank you guys. Next time we'll come back and continue.